how to get this going. All right, so hide this so we don't. Yeah, okay. Maybe this is gonna work. We'll see. So welcome back. What a crazy start to a term already. I think it's first two of school off. Yeah, it's like okay, how do we handle that? Especially one day is really a week.
Yeah.
So and then right away you get another holiday next Monday. So it's like Monday classes are, yeah, we meet like once for like 3 weeks. So it's like this is, so we had to get through a lot of stuff. I think I know everybody, or at least everybody know me. Yeah, okay. So this is the second class in the compiler, grammar compiler sequence. So we're probably gonna skip through a lot of the introductions since we missed last week. So I'm just gonna have you read the syllabus. And I am recording this. I have a student who has a class conflict. So she is in another lab on Monday. So I'm gonna have to record this. I'm trying Google Hangout on air, and there are two parts. So when we take a break, I'll pause it and publish that. I think they just publish this as a YouTube video. Then I'll send out the link to anyone, or I'll post it on Blackboard. Anyone who wants to go back and review the notes. So who knows? This might be good. I've never done this before, so I have sort of got my little microphone here. So we'll see how this goes. She won't be able to see anything if I'm going to put on the board. So I actually went through the slides I posted and added in more slides that normally I would put on the board. So hopefully when she gets it, or anybody go back and review this later, will get a better idea of what was said in class. Suppose I can turn on the video so anybody could see me right on the board too, but that's usually tough, trying to see clearly what's actually written. So I'll try to do everything in the slides. Okay, so this is compilers 320. I don't know the reasoning over any of the numberings in my department at all. So it was 229 for grammars and 320 for compilers. And you know me, I'm Sherry, and my office hours, let me just, so this is / week 1 and 2. So we're gonna try to cram in a lot of the stuff for the first 2 weeks and get you started with the lab. And we're actually not gonna worry about the homework, because that's week 4 and 5. So we'll be back by then. Okay, week 4, we'll talk about the homework and what's after that. So, but I want to get us at least, have a good idea of what lab 1 is? I actually broken it down into 3 smaller pieces, even though this used to be just one lab. Okay, the reason I did that in small pieces is a little bit more manageable, and I want you to really build one piece at a time. Okay, that's really what a lot of compiler work for this term is. So we're building like a small piece, and we add another small piece onto it, add another small piece onto it, and build something big, but just really are different components to it. And you may have to modify your previous component just a little bit to get this next component to work, which is kind of a good software engineering practice anyway, to kind of how do you actually make revisions and make changes that way. And if we have time, we'll do just a quick grammar reviews. It's been a little while, or if it's been a little while for some of you. And then the compiler overview. What are we doing in this class? Okay, kind of give you a roadmap. Where are we going? What are the things that we're going to cover? And really for lab 1, we need to talk about symbol table and the preprocessor. And if we get through all that tonight, that's great. Okay. Otherwise, I may have to make a recording and post it online later. This is the right class chat. Come on in. Let us see. And everybody's looking at the door and says, web development. No, this is not web development. Come on in. What's he doing? Still reading and signing? Okay. All right, so that's the plan for tonight. And somewhere in there, we'll take a break and have some cookies. And all right. So the syllabus is posted, and I took out actually all the slides that just talk about what's on the syllabus. You can read it, especially since you had me before, so it's not a surprise. So the 2 days, I'm actually here on campus for sure on Mondays and Tuesdays. So 36 are my office hours. Wednesday, Thursday, Fridays, I'm on campus for meetings usually. This Thursday, I will be here, for instance, there's a meeting. Sometimes I'm here on a Wednesday, but during the day, and very rarely on Fridays. But anytime you need it, if you need to talk to me, just send me an email and I could tell you how to reach me and how we can connect. And Saturday lab, traditionally for this class, and I don't know why, usually not a lot of people show up on Saturdays for lab. And part of it was because it was always winter and I always scheduled for like 8 o'clock in the morning. I know it's a big class. There's some seats up here. Okay. So I almost had nobody show up like all term, like for 8 o'clock on Saturday morning when it's ICL or whatever. So this term, the lab is actually in the afternoon, from 2 to 5. I know I'm going to be gone at least 1 week, one Saturday, or I'm going to be tied up in another meeting somewhere. One Saturday this term, at least one. And that Saturday, I'll just do Hangout for lab, for help if you need to, because I do have a way to get to the Hangout, but not actually on campus. But since your first part of your lab one, the part A and B are due this Saturday, if you do need help, I will be here this Saturday, right, from 2 to whenever people are still here. But if you just need to hang out, just talk, ask me questions, don't want to drive all the way in, yeah, just add my Google ID to your circle. Then you can always hang out with me or ask questions by email, whichever way. The phone, I'm only returning phone calls when I'm in my office. Okay, so if you just call me, it's usually hard when I'm not here in the office to return a phone call. So email is really probably the best way. And let's see, did I get through all this information? Okay, so again, you've had me before, so this is not a surprise. Now, I'm hoping this is it. All the bad weather just gone. Right? No more icy roads. We can't miss another Monday. Otherwise, we're kind of in trouble. But if the weather is bad, if they close campus again, or if it's just really dangerous to drive at night, when it's dark and icy, I don't want anybody to be, take a risk on the road. And I have to drive in all the way from Salem, so sometimes I can't get out of my hill either. So check Monday morning. I always send out my weekly welcome, kind of weekly message. So check Monday morning if I have to cancel class because I can't get here, or I'm going to do it by Hangout or something. David sent me a message. If I'm going to do it by Hangout or something, or just record it and post it, I'll let you know. So keep right. So before you drive all the way in, or if the 217 is closed again because we had that flood, or something, yeah, check with me first. Like I said, the class recordings will be available, so I'll post those YouTube links, and we'll see how this one goes tonight. And then just very quickly on the lab and assignment late penalty, not even going to track how many weeks, 20% penalty if it's late, but turn it in. Okay, don't wait. Don't like just, I'm not going to say, the first 2 weeks or something. Yeah, if you turn everything in at the end of the term, okay, I'll grade it. That's all right. But I prefer that you keep up with it. Otherwise, and really, if you miss the first one, you're probably not going to have enough to do the second one, which means you're not going to have enough to continue on. So, and with this class, especially the lab, you have to make sure that you stay on top of it. Otherwise, it's just really difficult to get it done. And you will get an automatic incomplete unless you don't want it. You'd rather have the F And I've never had student tell me that until last term. Students said, "Oh, I don't really want the incomplete." It's like, I don't get it. Okay, all right, that's fine. All right, so you will get it incomplete if you don't get the lamps and the project's done. So that's in the syllabus. So I just want to highlight that. Right, a few things in the syllabus. Other than that, so is there any general questions, any concern?
Textbook listed, do you need to get textbook?
Oh, good point. There is a textbook listed because we have to keep my syllabus pretty much consistent with the Klamath section, Klamath Falls section. I've taught this class for many, many years, and I have one favorite book, Parsons. It's about this thin. Most compilers' text is about this thick. Okay, this book is about this thin. Unfortunately, it's out of print. And whatever textbook I listed on there, that's optional. I don't want you to spend $150 or $200 on a book that we're only going to use a few chapters. I will give you some reference books you can check out from the library or uh, uh, Safari or something. And the chapters that you will need or the materials you will need, I think are pretty much in the lecture notes. But if you need the book as a reference, especially my tests are open book, open notes, and just like to have a book as a reference, pretty much any compiler book would do because the compiler hasn't really changed all that much. I mean, we learn something new all the time about any subject, but the idea of using the grammar to parse something, and that's really hasn't changed, right, since the 60s. So this is what we learned in the 60s and still applicable today, which is really kind of interesting with anything in computing. I mean, you 60s, yeah, nobody's touching that anymore. I mean, we're still the lessons we learned back then. And if you remember, I talked about that in grammar's class. Any other questions? Yeah, thank you for bringing that up. I always forget to mention the books. Okay, all right. So very quickly, and especially it's been a while since you had grammars. The three main topics that we talked about usually in grammars, and most of you was last term, was languages, machines, and grammar. And there was the idea of irregular languages versus context-free languages. And then these notations that you use to describe languages, the two notations that we're going to use mostly in this class are regular expressions for describing tokens. What do these tokens look like? What does an identifier look like? Does it start with a letter? Does it start with a number? Does it start with funny symbol? What does it start with, right? And then what can you have after that? Regular expressions will describe that. And then when we get to the actual syntax, so I have a bunch of these tokens. How do I make them into anything? What does an assignment statement look like? What does an if statement look like? Which tokens do I need where? Okay, that's really describing the structure of the language, and that's using context-free grammar is because for most programming languages, constructs are nested. If we do not have nested constructs, like if statement nested inside another if, inside another while, inside another whatever, if we do not have nested constructs, everything is flat. One construct followed by another construct, followed by another construct. Nothing is ever nested, then nothing is context free. Everything is regular. I can describe everything with regular expression, and I can parse everything using only finite automata, which makes it a whole lot easier. Nothing has to be remembered. Okay, I always say just like pushing these blocks off, right? They just keep, or having the strings keep characters keep coming at me. I grab them and then I just like move on, grab them and move on. I don't have to remember anything. And that's really what a finite automata is. As you go through these states, you're not remembering anything. You just keep grabbing them. Why do we have states? Well, they can tell me if I'm actually, right? I'm actually grabbing the right stuff. Okay, so if I'm expecting identifiers and you throw something else at me I don't recognize, well, there's no state for that, right? So that was the only thing, right? There are errors that could happen if you have, even if you have just a flat language. Well, none of the modern programming languages are flat. I can't get a whole lot done. So you do need context-free grammar. You do need what's called a push-down automata. Yeah.
Would assembly language be considered flat?
Would an assembly language considered flat? Um, let me think. Will you ever need to say, uh, probably, will you ever need to say, there's kind of the begin and end, right? I need to remember it, right? So I don't think so. I think it's simply, you may have flags, you may have to go back, but I think those information you can capture, and those are actually stored somewhere else and not actually in the syntax. Yeah, it's assembly language. I think so, because everything is pretty much, it's just like this is the command, these are the arguments you need. Yeah, maybe, right? So higher level languages, anything is usually nested. So you need to build, we are going to build a push down automata, which is really a big name for something that most of you probably have built at one time or another, a parser. So when we say we want to build a parser, we're really building something that recognizes a context-free grammar. But regular grammars or regular expressions is a subset of that context-free grammar. So even if I'm just building a parser for a regular language, okay, but the idea of a parser is it ought to be powerful enough to parse context-free languages, specifically these nested structures, keeping track. And really, there's nothing, just keeping track of the brackets, open bracket, close bracket, open bracket, close bracket. Okay, for the most part, that's the part you need to remember and make sure they match up. The A's, in grammar's class, we talk about A, N, B, N, the A's, followed by the B's. So make sure they have same number of A's, same number of B's. That's really all the parser needs to kind of keep track of. And the actual syntax, right? If statement needs to have, all these different parts to it. Where the brackets go, where the parentheses go. Do you need a semicolon or do you not need a semicolon? Most languages use a semicolon as a terminator of a construct or line. Assignment statement, boom, semicolon. Right? Followed by another assignment statement, semicolon, terminator. But languages like Pascal uses semicolon as separator. If you have two statements, put a semicolon in between them. This bottom statement does not need a semicolon if there's nothing else after it. Okay, well, how do I keep track of all of that in my head? Well, you don't. Those are in the context-free grammar. Your grammar tells you where semicolons are needed or not, where optional things could happen or not, variable declarations, data declarations. We talked about this last term. Data declarations have so many variables, different forms. Data declarations, you can have initialization or no initialization. So you can have int x, you can have int xyz. Within x, you can do this type of initialization. Within y, you can do this type of initialization. Okay, you don't want to initialize z, you don't have to. Okay, there's just so many different variables. You can have as many identifiers on the line as possible. So this tells me there is some sort of a recursive thing going on. Just like we did in the grammar, when we say, give me 1A, there's a recursive part. So if you want to give me more A's, well, just recursing on S. Keep giving me A's, and A's, and A's. So this says if I'm in the middle of declaring variables, and I could have many, many, many. So that means somewhere in my grammar rules, you're going to see this, a recursive term, not necessarily S, but the thing itself is going to have to recurse in order to get you more. Otherwise, you're going to get 1A. That's it. 150. Well, just apply this rule 50 times. You're going to get 50 of them. Okay? So that's why we use abstract symbols in grammar's class, like A's and B's and C's. But this term, we're actually going to expand that abstract symbol. This A might be comma ID. If this A were comma ID, I'm recursing on that. I'm going to get comma ID, comma ID, comma ID. Keep going, keep going, keep going until I don't need any more. Usually there is a lambda that says, okay, no more. Cap it off. No more. Okay. So, but lambda also says I don't need to have any. Lambda means none, empty string, nothing. Okay, so if I have just one X, that's fine. I don't need any more. Yeah, but if I did need more, and I don't know how many more I need, that's the part that gets recursively generated. Okay, so context-free grammar is recursive. Okay, there's a lot of recursions going on in there. And week 4, when you come back, we're going to talk about left recursion, right recursion, and why that's different. Right? So this is right recursive. S goes to low a, big S. S goes to big S, A. If I'm just doing A's, no difference. I'm still going to make a bunch of A's. Okay? This is called left recursive. That means I'm recurse first, and then there's something after it. Recurse first, and then something after it. Okay? Makes no difference on the string that you're going to get ultimately, but makes a huge difference what type of parser you could build with this type of grammar. Okay? This grammar, the first one, S goes to AS, will allow you to build something called a top-down parser. That is, we actually start with the S on the top, and then start peeling away the A's, coming down. This, the S goes to big S, recurse on the left, is actually what's called a bottom-up parser. I am not, otherwise, if I do this top-down, I don't know how far I have to go. Okay, so in fact, what I'm doing is I'm grabbing the last A. If I need more, okay, give me another one. If I need more, okay, go up, give me another one. Go up, all the way up to the root. When you don't have any more, that's when the lambda kicks in. Okay, so, I mean, just flipping the symbols. All of a sudden, I can't use it anymore. So I have to change the grammar so I can actually use it. So when you come back week 4, we'll be talking about something called the grammar transformation or modification. Really easy. It's not math. It's really easy stuff. But if your grammar is not in shape that you can use it, we cannot build an efficient parser. And that's really our goal this term, is if we just take a quick look at the components of a traditional or conventional. Compiler is actually just one part of it. Compiler is just a term that was left over from the 60s. Most textbooks call them translators now, and really is translator. You gave me something, I went through this little box, and then something else comes out. Modify. Okay, so a conventional translator like Microsoft C++ compiler as we know it takes your source program that you typed in, your .cpp file, and actually goes through the preprocessor first, okay? Because there's actually a lot happening in the preprocessor. We're simplifying that. We're doing the pound define, that's it. but there's actually a lot going on in the preprocessor. And part of that preprocessor processing also involves lexical analyzer. If you don't read it, if you don't break it up, how do you know what do you have? So it does involve like reading it, reading these things and say, oh, that's needs to be preprocessed, that does not need to be preprocessed. But preprocessor works on a line unit, a single line. A preprocessor directive must be the first thing. You can have some white spaces apparently, but must be on a line by itself. So you couldn't have a bunch of statements and go, oh, I really like to do a pound now. I won't let you do that. Okay, so the pound has to be the very first non-white space on a line, and it can only be on that line. I can't break it up into two lines or anything like that. Okay, so there's some rules about these preprocessor directives. But preprocessor, after it's done, then we talk about actually what happens with the preprocessor today, real quickly. I'm doing on time. Good. Okay. And then it actually produces what's called the modified source, and that goes into the compiler as we know it. And we're going to expand that box and look at the different components of it. And it produces a target assembly program. And it goes through the assembler. Assembler is another parser. Okay, so Random said, well, what about assembly language? Well, I'm still going to have to read the assembly language. It might be a little easier to parse if it doesn't have the nested structures and I have to worry about begin and end and stuff nesting within each other. But still, I need to know what are the, what are the instructions and what do they take? Okay, so these are rules that, and then I got to figure out what that means. What is it, all this bunch of these instructions actually mean? So it needs to produce the machine code and goes through the loader and the linker, and that's beyond, right? The bottom two boxes is really beyond this class. If we did have an advanced compilers class, we might look at assemblers, how to write one, and do the linkers and loader. In graduate school, they usually get to, if I have, in graduate school, the first compilers class will focus more on the back end. This optimizer code generator boxes over here, which we're just going to barely touch on or not even just mention. We probably won't have a lot of time to go through that. And then the second course in the compilers, if there was a graduate level, they will head the assemblers and the linkers and loaders. Okay, so that's why most compilers text is about this thick, because there's a lot of stuff going on in there. Question?
Get into the in memory.
Memory is part of memory management and stuff like that. Yeah, it's part of the code generator and all part of this processing here. Ooh, some of these came out dark. Okay, so the four main boxes, or five, of the preprocessor we're going to do too. So preprocessor, and then when we get the preprocessed text into the compiler, the lexical analyzer you already have, or at least a first cut, mostly done, like 90% done. Your part or your lab one is going to add a little bit more to it. If you do not have a lexical analyzer done yet, please talk to me. And then I had some slides that I went over on Saturday about what you need to do to get one of these things done. Otherwise, you don't have enough to work on your lab one. Okay, so, but what comes out of lexical analyzer after we're done with lab one, pre-process, and we're going to add a few things into lexical analyzer, are a list or a vector of tokens. That's it, tokens. We're not going to see the original text anymore. That file, we're not going to see that anymore. Okay, we just have tokens. Okay, and then when that goes into the parser, then we take these tokens and try to make sense of them. I have an ID, I have an equal sign, I have a number 10, I have a semicolon. Okay, then I'm like almost like matching, right? I'm looking at my grammar. At this point in my program, I'm expecting, okay, what does it look like? X equals 10, semicolon. Oh, assignment statement. Okay, can I have an assignment statement at this point in the program? Well, if I'm inside my curly brackets, inside of a function, okay, my grammar is going to tell me yes or no. Okay, so parser is a yes-no machine. Is this syntactically correct or is this not syntactically correct? And then actually reporting the errors is a little harder. Okay, you can say yes or no. Okay, it's easy. And report, and when you have an ID, you actually have to like take them to where the error is. You know, when they double click on it. Okay, that's part of the IDE. That's actually a little bit more work. But for our purposes, okay, we're going to give them minimal error messages. We're not doing an ID. We're not taking them to the error. We're not even telling them what line number it is. Okay, so just kind of minimal amount. So they made a mistake somewhere along the line, but at least we can say, yep, that's not syntactically correct, or yes, that's yes or no. Okay, so that's what we're going to do, and we're going to touch on semantic analysis, which is after, yeah, this is syntactically correct, but what does it mean? Right? Is it type correct? Did you declare the variable before you use it? Right? And I see Colin had a question for me Saturday. I have a number, but that's beyond the size of an integer. I have an integer, but it's too big. Okay, is it my problem, compiler's problem to catch that? Or is it the programmer's problem? You type in a number that's too big. Who takes care of that? Okay, so, well, if compiler cares about that at all, that's not syntax. Syntax syntactically just says, I need a number here. If you give me a number that are beyond, I have a 32-bit machine or whatever my memory is, I can't, that's too big. Well, that's not really the problem of the parser. Parser just says, I need a number, give me a number, okay? But before I send it on for code generation and have them actually run it, if I'm really, if I could check it, I could stop it and check it and go, well, that doesn't look right. That's way too big for 4 bytes or however many bytes your thing is, right? So yeah, you can catch that. Well, where does that happen? The meaning of the thing, semantic analysis, that's where it happens. And then it produces something. We're always going to come back to this roadmap without this extra stuff. But I just said, how do I tell if I actually declare the variable before I use it? So that means that information is not in the grammar. Grammar is long. If I say int x, and 10 lines later, I said x equals 10. That declaration was a long time ago. I've seen it, I processed it, yep, declaration, but it's long, it's gone, right? So, and I can't just say, well, let me see if X was declared. Let me go back like 10 lines. What if it was declared in another file, right? How do I know? How do I go chase this thing down? I don't, that's too slow. Efficiency, that's what I'm going at. Go, 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 go. I'm not gonna waste time. I've seen it, gone. Well, I better store that information somewhere, and that's where the symbol, that little dark blob down there, gotta change the color on this projector. The symbol table. Mine looks good, but anyway, I'll change the color. Symbol table comes in. Yeah.
So is that why if you don't declare something, it's a linker error instead of like an error during compilation or during like the previous steps?
That's only for functions.
Oh.
Because functions could be in a whole nother file. But if I said, x equals 10, but I never declare x in this function, it catches right away, right? But if I say, I'm going to call function 1, and I gave you a prototype for function 1, but I never actually define function 1, well, that actually, the linker, the compiler, the single .cpp file, I don't know. It could be somewhere else.
Does the symbol table have some sort of level that it records as well?
Levels like scope and stuff? Yeah. Yes. There's a bunch of stuff that get thrown into the symbol table. Okay, so for our lab 1, we're just going to build a very simple table. In fact, for our lab 1 symbol table, I want that symbol table to work with not the parser. We're not going to worry about decoration, variable decoration, function decoration, none of that. We want it to work with the preprocessor. Right? Preprocessor, you said pound define max 5. Where does that information go? Well, it goes into the symbol table. Okay, so symbol table keeps track what type of thing that went in there. In this case, max is a constant, right? A literal constant. But later on, when we get to the parser, we're actually going to bring the symbol table back and say, okay, now I have x, which is int. Remember that. So when I get to x equals 10, at least it tells me, yeah, x is, I've seen x before. And the scope. We know C++ is terrible about scope. You add a curly bracket, you have a new scope. You add a curly bracket, you have a new scope. Well, that scope information is also stored in a symbol table. Well, not the scope itself, but the variables defined in that scope. So you can have x, 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 4 x's, 4 different scopes. So there are 4 entries in the symbol table for x, and they each have a scope number. And compiler, there's really like no great mystery about. It just uses number to keep track. You're in the outer global scope, 0. As soon as you enter one set of curly brackets, you're 1. You enter another set of curly brackets, you're 2, right? But those also are tied into a particular function. X defined in main is different than X defined in function 1. Okay, so it keeps track which function am I in and which scope am I in. And there's almost like, okay, I've done with function 1, function main. I don't need to see function main again. I've got all the information I need out of function main. And local variables within function main can never be used by anybody else. Right? So basically, I'm done. I don't need that information anymore. Okay, so there's a lot of considerations. So we're going to build a very simple one, lab 1A. Very simple one. I'll tell you what should go in there. And then like week 7 or 8, we'll pick that up again. Okay, in the semantic analysis, let's bring the symbol table back. It has a lot of stuff in there that I might need, like type. If X is int, I'm assigning it to something else. Well, there's a type issue here. Okay, I can't assign it to a string literal because it's defined as int. So I gotta kind of match those up. I expanded those 2 boxes, the lexical analyzer and the parser, because that's how they tied in with some of the grammar stuff. Lexical analyzer is a finite automata. It uses regular expressions to define tokens. And the structure of token is concatenation. How you slap them, how you concatenate this thing. Right? What does one of these tokens look like? Well, how many characters do I grab and say, okay, this is a token. Concatenation. It's regular. There's no structure to it. It's just like one after the other. Linear concatenation. Parser is a push-down automata. And the push-down part, later on, we'll see is a stack. I need to store something. Like I saw 1 curly bracket, well, throw it on the stack. I saw a second one, okay, open bracket, throw it on the stack. When I hit the closing one, I pop it off the stack. I saw another closing one, I pop it off the stack. Everything matched up. A's, B's. A's go on the stack. When you see a B, pop off the A, pop off the A. Okay, we did that a little bit in chapter 14 last term, but a sort of abstract model. If we were to implement that abstract machine, it would be way, way, way too slow. Okay, so that's where I think some of our focus this term is. How do we actually build an efficient parser? We're going to look at 2 of them. One is both of them happen to be top down. I'm going to skip over the bottom up one because usually we use a tool for that, and we're not going to write one by hand. Okay, so I'm going to show you what a tool looks like. The top, those 2 parsers are 2 different techniques. But you can see that, once you have the grammar, the program itself, the parser itself, almost can be generated automatically from the grammar. And that's why there's so many parser generators out there. And they're all based on grammar. You gave me the grammar, I will give you a parser. Right? That ultimately, that's where most professionals use. But there are circumstances where that tool does not help me very much, because I really want to incorporate that as part of my other projects. So if I'm doing a game, I have a very small language that I want to parse. I don't want to go pull out this, Lex and Yak tool, which is called Lex and Yak's tool, which generates this gigantic thing for me for C++. I only have a very simple language I could handle myself. Just show me how to build a quick parser, which that's where my focus is. Okay, how do I build very simple top-down parser just based on grammar, so I'm not going to get confused. Do I need a comma here? Do I need a semicolon here or not? Everything is in the grammar, and it should just pop right out, just generate itself. Okay, and you can see, and I hope you like both those techniques I'm going to cover, because it just seems so easy. I have the grammar, here's a parser, boom, it's done. Okay, so all right, so that's kind of our roadmap, and we'll keep coming back to this. I'm almost like marking off the boxes. Lab 1, we're going to do simple table. We have the lexical analyzer. We're going to do the preprocessor, okay? And then lab 2 and 3, we're going to do the parser, and there's a project at the end, which incorporates a little bit of semantic analysis and maybe, a little bit of back-end stuff. So the stuff, those optimizer, code generator, and target code, that's the back-end compiler. Semantic analysis, parser, and lexical analyzer, that's called the front end. I have another graphics. I actually labeled them. There are a bunch of terms. But I think I'm more concerned today, since we have so little time, to make sure that you have enough information for the lab. And then we can always come back to the concept later when we come back week 4, a review. Okay, so tonight is almost like, okay, let's worry about the what. And then when we come back, and the how. And then when we come back, we can talk about a little bit of why if we need to, okay, to kind of tie everything together. So you should already have a lab from the grammars class that did, first of all, you should already have a language picked out that you're going to use for this class to parse, the language for your project that you want to parse. The labs themselves have to be written in C++. You can use STL, you can use any library you want, that's fine, but it has to be written in C++. And for the lexical analyzer, I'd rather have you use the techniques we cover for building a finite automata rather than using the regular expressions library, that's built into STL. So there's a little bit of learning curve with that one too. But really it's quite simple if you just follow the finite automata. So what did we do in lab 1? Or what should you have at this point? Well, you should have a language picked out. You should have a little sample program. You feed this little sample program through your program, and it should recognize identifiers. And for simplicity, in grammars class, we just said anything that's just letters and digits and underscores, yeah, that's an identifier. I don't care that ends is a keyword and wild is a keyword. We didn't do any of that, right? And we recognize numbers if you have integers and floats, okay? Operators, and you can decide to support these complex ones or not. It's your language. You decide what is your vocabulary, so to speak, right? What is your token? What are you going to support? Should have some logical operators, otherwise if statements will be really difficult. Symbols, okay? And preprocessor directives. And we just did the pound define. We're going to talk about pound include. We're going to talk about pound if. We're going to talk about all these other ones. For our lab, we're just doing pound define. Okay, so And then white spaces, we pretty much just ignore them. We read them and go, yep, okay, white space, I don't need to save it. But everything else is stored in some kind of a data structure. I use a vector for mine. If you use a list, it's sequential. It's sequential. So whether you use a list or vector, doesn't matter. Okay, so just one after the other. These are all the tokens. Hopefully you have this much. What we did not do is we didn't determine which identifiers are keywords or reserved words. In concepts of programming languages, and although this is very, very unusual, there is a difference between keyword and reserved words. Reserved words are those words that you cannot use as your identifier, your own name. Okay? And keywords are those words that have a special meaning in the language. C, C++, and most modern programming languages decide to lock the keywords as reserved words. Okay, they decide to lock it. This is okay. Int is a keyword that means integer decoration, but it's also a reserved word. You may not have a variable name called int. That's mine. You can't use it. Okay. And that makes the compiler's jobs, the whole compiler writer's jobs, a whole lot easier. Imagine that's not the case. Imagine that's not the case. Int. First int is a keyword. Second int is a variable name. Then it's purely by context. Where is it? Okay, you cannot tag anything unless you know where is it. So if you say int equals 3, right? It assumes you mean the variable name int versus declaring yet another, right? Yet another variable of the type int. I just trying to get this clear in your head, right? It's just a nightmare.
Do they do that for ease of making the compiler or for ease of programming? Because it can handle that just fine if you're using custom types.
Yeah, well, I'm not exactly sure why they make the distinction even between keywords and reserved words, or why some languages, I can't tell you one right at the top of my head, some languages will even allow this. I'm not even sure this makes it that much easier to write. Seems like it's very confusing for me to keep track, right? My namespace just kind of explodes because it's being hard. Sometimes it's, yeah, that definitely makes the compiler writer's job a whole lot harder. Very, very difficult.
If you have a custom class, though, it'll handle that case just fine.
Probably. Okay, yeah, it could. I mean, we could, yeah, we could do that, yeah. But C++ though, even you say, I really don't like the int that came, right? The base type int that came with it. I really like to customize it. I want to write my own int class. Okay, it won't let you, the word is locked, it's reserved. So you couldn't define a class called int, right? Even though it's yours, right? So most cases, most languages you deal with, keywords are reserved words. We're not even going to worry about that. We did not pre-process the pound directives. I think we grab them as tokens and say, yep, that's a token. That's a token. We'll deal with it later. And then we didn't really add any comments. I think I told you now, don't worry about comments for now. And there are different types of comments, of course. We could deal with it. So based on, and I looked through your lab, I think some of you handle the preprocessor directives a little differently, and I'm not exactly sure what I told you last term on how to handle that. Either way, it's probably okay. The reason that it's a little tricky with the pound define is pound define could have a symbol and a value, or it can have a symbol with no value. And the value is not necessarily typed Right? So when you say pound define max to be something else, that something else is just a string. Right? Most cases we define them as constants, like max is 5. So later on I can substitute 5 for the max. Pound define doesn't know that. Pound define says this is pound define. The first thing I encounter is bunch of is a string. And the second thing I encounter is a string with a new line. But if the new line appears before I hit the second bunch of strings, that means I just have a symbol. Pound define a symbol. And you do that all the time. Pound define include underscore H files. You do that all the time because you don't have to give it a value. It's just saying, I've seen it. I've seen this include file already. So if I come back to the same place again, don't let me include this again. That's why you have the if not defined, defined it out, right? Otherwise, how would you know if you've seen it? Well, I defined it. Where does it go? Goes in the symbol table. So we'll talk about a symbol table. All right, so if you grab pound define as a token, max as a token, and 5 as a token separately, when you did your lexical analyzer, then that means we'll also have to save the new line token. Right? So it means you got to go make some changes. You still have to save the new line token only for pound define. All of the other new lines, they don't care. The whole thing could be on one line. Any line breaks at all, perfectly fine. Okay, only pound define has to be on a line by itself. So I got either capture that new line token or grab this whole thing as one token. Pound define, space, max, space, 5, boom, there's my token. As soon as you hit pound, grab everything after that till you hit the new line, then you have a one long token, string, right? Just a string. You can tag it as a preprocessor directive or whatever. Then part 1C, your lab, 1C, we're going to read that information and break it up. And it seems like it's extra work. I didn't mean to do that. Let me come back up. Let me bring this slides back up. It seems like extra work. But remember, preprocessor is almost always a separate tool by itself, right? So I mean, we are sort of combining them because we're reading the same file. Why read it twice? Well, preprocessor usually has to do it twice just because when you do stuff like pound include, which inserts a bunch more information, right? There's a lot to process. Lexical analyzer, when it gets it, is that everything, all the other junk, everything else have been processed away. I'm only looking at the program, the part that I care about. Right? So I don't want to see anything else. So, but we sort of jump right in and say, oh, let's build the lexical analyzer first because that's easy. Because I'm just breaking things into tokens. Right? Then, oh, okay, let's not worry. Now let's worry about what would you have done had you started out with a preprocessor. Well, had you started out with a preprocessor, we're not going to process anything else but that. So that means we're going to read in the pound define max 5. We're going to skip over everything else that has nothing to do with max. Till I get to the max, I'm going to yank the max out and put a 5 in. Right? It doesn't even know that 5 is actually a number. Okay, lexical analyzer is going to tell me that 5 is a number because, oh, look, digit, number. Okay, so, right, and it's going to max a couple times. It's going to yank that out and put a 5 in. Then the pound define is gone. I'm just going to left with int main and then everything else process. Then the lexical analyzer gets it and breaks it into nice tokens. Okay, so we kind of sort of did this just because we're at the end of last term. We didn't have time to really discuss preprocessor. And that was always my dilemma with the sequence of classes is like, we know how to do a lexical analyzer, but we don't have enough information for the preprocessor. So let's just build that piece and then add the other piece later. But I think I like, I'm sort of combining the two So everything else is just tokens except for the pound define. Okay, so that's how we're done so
when
far.
it's processed, you wouldn't say like pound define is a preprocessor and max is a ID and the 5 is a.
Yeah, so
You don't break it
probably,
down like that?
yeah, so no, I think,
You always keep it together.
yeah, if I would probably just grab that. Yeah, I will probably, I think in my lab, I would just say grab the whole thing and says, okay, that's preprocessor. So I'm gonna let preprocessor worry about that. Because max is really not an ID. Well, it's an ID, but it's really not like a variable or anything. It's a constant. It's a constant name, right?
Constant name, yeah,
Right.
okay.
But then as soon as I pre-process this file, max is gone. I'll never see max again.
That's why you keep it
Right.
together.
Yeah, so I kind of keep them together, so I don't have to worry about this line break, right? I think for your lab, you just say, okay, int ID, main ID, open print symbol, close print symbol, open parentheses, close bracket symbol, ID, symbol for operator, whatever. You print all that out for me. That's the lab. Okay, so now we're gonna go a step further. So in lab 1, well, the very first thing you do is actually build a symbol table. So then we talk about the second thing, the 1B. Both 1A and 1B are small, and they're due this Saturday midnight, Saturday night. So if you're struggling with it for any reason, come to lab on Saturday and we'll look at it. And then part 1C, because we don't have class next week, is actually due the following Monday. The reason I make it due Monday is, well, I usually like to see a run. But I also usually have like 15 students and compilers instead of 30. So we'll see how about checking off. I want to, I'll take all night to check everybody off. So we may do some check off on Saturday. I don't know, or any other time during my office hours or something. So I like to see a run. At least have you tell me what you did. Okay, so I always have a check off sheet for the lab, so you can say, okay, show me these 5 things, and then that's how I check you off. Okay, anyway, that's jumping ahead.
Do you want an
Question?
internal table or an external table?
Uh,
Keywords, do you want an internal table or an external table?
Meaning, is it hard coded in the
code,
program? Okay, I like the static table in the code is probably just fine. Okay, all right. So let's add those pieces. Okay, that's is with some pound defines. Okay, pound defines. Yeah, pound defines. No, not necessary. No, not pound defines. Const. You can have a const static table in there. Okay, so we have to deal with the preprocessor directives. We have to worry about the keywords. Okay, and I also want there's something I want part 1B. I want you to tag the tokens. I want you to tell me what type of tokens they are. Are they IDs? Okay. Are they commas? Are they semicolons? Are they int? Are they if? Are they the actual keyword? So instead of just saying, oh, that's a symbol, what type of symbol is it? Is it an open paren, close paren, bracket? Because the actual thing, the actual string or character is going to show up in grammar. So if I'm going to try to match this thing later, okay, I'm going to looking at see how to match this thing. I needed them to actually tag in the data structure. So right now I have a list of tokens in my data structure that just has the value, the string, the int, the main, the quote, the open paren, the semicolon, the greater than sign, whatever it might be, the actual text. But I want also another field associated with that token that says, that int, that's really a keyword int. That main, that's really an ID. So now all of a sudden I have a keyword int, I have an ID, I have an open paren. If I look in my grammar, yeah, sure enough, there's something that requires a type like int, something that requires a main, which is ID, right? Okay, yeah, everything starts to match up if I know what I'm looking for. So in this case, the int might be actually a type, a data type. if in my grammar I'm requiring a data type at that point. Okay, so we'll talk about how to match up with the grammar later. So this is also part of the slides where I wanted to cover last week. Okay, so I may have to jump around a little bit. So last week I was actually going to do like a review of grammar. So define a regular expression that describe W, V, where W is just zeros and ones, but V is 0, 0, which means it ends with 0, 0. Okay, so this one, there's, do this for the person who can see. So this one is really, 0 or 1 star, right? It's any number of zeros and ones followed by 0, 0. So regular expressions is that. It's concatenation. Tell me what pattern you want. They're just like one concatenate one after the other. So there's no big surprise there. And the finite automata, I'm actually not going to draw. I think you probably get. So I want W to contain 3 consecutive zeros. So I need 3 states, 3 consecutive zeros. Okay, so if I don't have zeros, they have ones, then I have to go back to the start and make sure I can have 3 consecutive zeros, 3 zeros, right? Actually, I can put, since I'm going to write. And context-free grammar for a palindrome, an even palindrome. So you have zeros and ones, you have the 0 and 1 reverse, right? So you have 1, 0, 0, 1 is a palindrome, 0, 1, 1, 0 is a palindrome. So whatever the first pattern is, reverse it and concatenate them together. You have a palindrome, which is the same, you read same number forwards and backwards, right? Okay, so the context-free grammar for that is actually, well, actually, I'm going to do that. All right, it's actually pretty easy. So this says, well, this one is equals, okay, so this says, yep, if I have zeros, then I better have zeros to matching. Have ones, I better have ones to match, right? If they match, then it's gonna be the same forwards and backwards. So I'm gonna have a palindrome. So, and I won't worry about that. You can look through those, and if those are not familiar and you go, I don't know how to do that, let me know. I can certainly cover that. And I'm repeating some of the slides because I wanted to cover that earlier. I was talking about the labs. This class really pulls a lot of things together. I mean, data structures. You really have to think about data structures. I just asked you to build a symbol table. What should the data structure be for that symbol table? Okay. And, well, some considerations. How fast do I care about insertion into the symbol table? Should the symbol table be sorted? Should it be a tree structure? Should it be a hash table? Okay. And also, how many symbols realistically do I have in a typical program? I'm not going to have 1 million symbols. How many variables and functions am I going to have? A lot, probably, for a large program, but probably not like that many. So if I optimize my data structure to handle large amount of data, it turns out I only have like a handful of variable names, and right? I just waste. I mean, I really don't need that. Right? So things like that, right? Consider, well, what should the data structure be? How about your keyword table? May I just ask me, should it just be hard-coded? Yeah, your keywords is static. It's not going to change. If you're going to start out with 15 keywords, you're still going to have 15 keywords. And if you really just have 15 keywords, even if it's a linear search, INT, are you in my list? Well, go find it. It's not going to take that much time. C++ keywords are actually quite a bit more. So, and I know how many they are and what they are. If I keep them sorted and do a binary search, I cut down a little bit on the search time. I'm looking for speed here. I can waste memory since I do usually have a little bit of memory to waste, but I cannot really afford the time. I'm not going to have someone hit Bill and then sit there and wait. Okay? In fact, the IDEs are so good now. As soon as you type in a wrong key or wrong character, it tells you, oh, there's a syntax here, right there. Right? How does it do that if it's going to take a long time to think about it? It can't. It got to go really fast. I can't have them type in something and then 5 seconds later, oh, wait, there's a syntax here there. I didn't see. Okay, so it really goes really, really fast. So I'm really worried, concerned about, Go. If I type in INT, space, INT, semicolon, I'm going to get an error right away. Right? How does it know that? Well, it's going to have to go search in the keyword table somewhere, right? It's got to know that INT is the keyword. You cannot have it as a reserved word. You cannot have it as your variable name. How does it even know I'm trying to declare a variable name? Well, you have a type. You have something else in a semicolon. It looks like a variable declaration. So it has to go to the grammar and say, oh, something that starts with a type, and then maybe an ID and a semicolon after that, variable declaration. So it has to go really, really fast. Okay, so I'm gonna just talk a little bit more before, and I already talked about this. The type of parsing we're doing, or the type of compiler technique we're covering, really deals with a one-dimensional text. Even though it may format nicely, and yes, the preprocessor does require the thing to be on a line by itself, but that just simply means I need to capture that new line character as a meaningful token. Right? That new line character cannot be thrown away because it's a white space, but still it's a one-dimensional text. So I may have pound define, new line, and keep going, keep going, keep going. Okay, so the technique works if you have one-dimensional text. And we can go through this. Oh gosh. Okay, so you can probably read some of this. There are different types of compilers, there are different types of applications. So I don't know why this slides keep popping up. Simple table, but I think it's probably a good time to take a short little break. So when we come back, I want to talk about simple table, a little bit more about preprocessor, and then a different type of thing usually happens in a preprocessor. We're only going to do very minimal of it. And then what lab 1A, 1B, and 1C looks like for you, and what you need to do. And then if any questions you have. Okay, let's take a 10-minute break. Let me stop.